Hey guys, my name is Sandeep Patel. I'm here to teach you the space complexity today. In this video, we are going to cover space complexity in very depth. I hope you will like this video. Um, Alright, so let's begin. So let's start with the very basic terms, right? So the computer, they comes with the limited amount of memory, right? So each computer has a different space. So let's say, for example, one computer might have like 2 gigabit of RAM, the other one might have like 4 gigabit, maybe 16 or 32 gigabit of space, right? Um, so there's a limited space provided in the computer, right? So whenever we write a program, we need to make sure that it should not take more space than what is provided in particular computer, right? If it takes more space, then what happens is your program will hang and then it will fail, right? So that is the reason why we need to care about the space complexity of our program, right? Whenever we write a code, we should care about how much space it's utilizing. If you don't know the precise number, that's fine, and that's the reason why we're learning big O space complexity, because in big O space complexity, what we're concerned about is the bigger term. We don't do like the exact space calculation. It roughly gives us the worst space complexity that our program runs on, and once you know that, then it's easier for you to optimize your program so that it can effectively use the space without exhausting, right, and then failing. All right, so let's learn about that. Okay, let's take an example here. So the space complexity measure how much additional memory an algorithm uses relative to input size, right? So let's take an example here. So let's say that you have to deliver a package, right? 100 package, right? So you can choose a scooter to take one package at a time, or you can have a truck that has like space enough to store 100 packages and you deliver at the same time. So in terms of space complexity, what we're concerned about is here is the less memory that takes. When we write a code, we need to make sure that our program takes less memory as possible. So in this case, I would say that this uh, taking one package at a time on the scooter is efficient, right? Because it occupies less memory. And in this case, you need a space to accommodate 100 packages, right? So that takes up more space. So whenever we count the space complexity, we should look for this. So we should look for variables that takes up space if they are growing um, dynamically with the input size, then we are concerned about that. So right, when we calculate time space complexity, we should look for variables, we should look for call stack. If return statement returning any variables, we should also look for that. um, all right, so let's take an example. Let's say this is a piece of program, right? And it has some variables which occupies 1 unit of space. There is a call stack which is called for one time, and so that takes 1 unit of space. Let's say there is a return statement which returns some variables. Maybe that takes 1 unit of space. So this is important when calculating the space complexity, right? All right, so let's start learning more in depth. Okay, so in so let's look at the big O notation first, right? So what is a big O notation? So big O notation tells you how much slower a piece of code is, right, when input size is larger, right? So big O does not care about the number of operation, but it cares about how much space it occupies, right, when the input size grows. So for example, you have a piece of program that takes some input and produce some output, right? And each program has multiple operations or maybe statement. So for example, this is the program, this is one statement, two statement, or you can say there are two operations happening in this program, right? So what is the big O complexity? Is basically finding out the total space that this particular program takes, and that is what is the worst space complexity that this program takes. That is what the big O is all about. All right, so let's learn about this in depth. So let's say that you're given a program like this, right? This is a very simple program. What it does is it takes some input here, right? And then it just return, right? So this is one statement. So you can consider each statement when there's a variable return or a call stack as one unit of space, right? Um, so how do you draw this on the graph, right? So on the left side you have unit space, and then on the right side you have input, right? So this input n, let's say that right now this n size is maybe 100, right? So let's say right now n equals 100. In this case, what happens when you run this program? So when you run this program, this line of code is executed only one time, right? So we can put this in here. So this takes one unit of space, right? And what happens when size increases? So let's say now n increased from 100 to maybe 200, 500, maybe 100,000. So in that case, this statement is still going to run single time, right? So if we put it here, and that when n grows like this, maybe 100, 200, 500, maybe 10,000, it's gonna go like this, right, in a straight line. And that's the reason why the space complexity is constant space O1. Alright, so next, linear space, right? Okay, so let's look at the space complexity of this program here, right? So we have one variable, right, which is a copy, and we have this loop that runs from 0 until array length. And what is array length? So array is the input, right? So you can say, okay, n equals array length, right? So this loop start at 0, like somewhere here, and then end when n becomes array length, right, like somewhere here, right? And within this for loop you have this variable, right, which pushing element into this array. So now this array is dynamically growing in size, right? When we initialize this, it has one unit of space, right? Maybe for example here somewhere, or maybe let's say 0, right? Because it's empty, let's say it's occupies 0 unit of space, right? But when it grows dynamically, let's say I equals 1, at that time this statement runs one time. When I equals 2, when n equals 2, this runs at 2 unit of space, right, until it becomes n unit of space, right? So when you plot the graph, let's say when I equals 0, both are here. When I equals 1, let's say I equals 1 here, and n equals 1 maybe here. In that case, it's gonna grow like this. Let's say when I is 100, right, at that time this statement will also run 100 times because it's within that for loop. So it's gonna occupy like 100 unit of space, right? So graph goes like this, and finally if you plot the graph, it's gonna go linearly like this, right? Okay, next. Alright, so we're interested to find the space complexity of this program here. So we have this variable declared here, which and there's a for loop which start at 1, right, and then it stop at n when n, as n is what, input here, right? So it stop when I equals n. But look at this, now I is multiplied into 2, right? What does it mean? So let's take an example, simple example here, right? So what happens when this statement, which takes 1 unit of space, is within this array? Let's say I equals 1 here, right? At that time this variable also occupies 1 unit of space, right, here. And then next time the I becomes 2, right? So let's say when n becomes 2, this also runs 2 times like this, right? And now suddenly the I becomes 2 into 2, which is like 4, right? Now n is here, while this this variable is running only third time, right? It's somewhere here, right? And then when next time it goes, so 4 into 2, which is 8, right? So when n goes here, let's say n equals 8 here, right? That time this code will be running fourth time, right, which is somewhere here, right? So the graph goes like this, right? When you plot it on the graph, it's gonna go like this, right? And that's the reason why it takes logarithm space, because we are jumping 2 raised to k minus 1 steps at a time, right? Like for example, when I equals 1, let's do it here. So when I equals 1, and then I goes 2, and then second time it becomes 2, and the third time 2 into 2 is 4, and the 4 into 2 8, right, and so on, until at the end what we get is, if we want to find the kth term, that would be 2 raised to 2 raised to k minus 1, right? What is this kth term? Let's say there's a fourth iteration going on, so k becomes 4. So 4 minus 1 is what? 3. 2 raised to 3 is what? 8. So you can say, okay, 0, 1, 2, and 3. So the third iteration has a value of 8, right? And using this equation, so when loop stop, when I greater than, when let's say when I becomes this loop runs until I is less than n, right? When soon as I becomes greater than n, then it stops. So if we take this kth term, right, which is, we're replacing I with kth term, less than n, right? If we take a log on the both side, so it becomes k minus 1 less than equals log n time, right? Which means that k runs for log n time, right? And that's the reason why the space complexity of this program is log of n. All right, and for this program, we can quickly estimate. So we have this one variable here, so at this time it takes maybe, let's say, 0 unit of space, but then soon as it hits this for loop, we're interested to know how long this for loop is running for. So it start at 1, so let's say somewhere here it start at 1, and then it ends when input is what? Array, right? Array length. So n equals array length, right? So which is here somewhere. So loop runs from 1 until n, and at the time it's jumping 2 steps at a time. We just found out when it jumps 2 steps at a time, it has a log n iteration, right? So this loop takes log n iteration. Their inner loop runs from 0 until n, and it goes 1 step at a time. So in that case, it's going to run n iteration, and this statement takes 1 unit of time, 1 unit of space, right? And if we find the overall complexity of this loop, so it would be log n times n into 1. We don't care about this one. Why? Because we are only interested to know the big terms in this program, right? We go concern about the upper bound. Upper bound means what is the highest complexity, right? In this case, let's say this return statement takes 1 unit of space, right? But this code is higher in terms of complexity. This takes n log n time, which is higher than 1. So we just ignore this part, and we're interested to know how linear, how much space this particular code takes in our program. All right, next. Okay, so we're interested to know the space complexity of this program. We have this variable here. We're interested to know how long this for loop runs from. It starts at 0 and it ends as when n becomes array length, and it goes 1 step at a time, right? And when that happens, there's another loop is also running n times, and there's a one operation inside which takes 1 unit of space, which is multiplied n into n time, which is n squared. So we know that this variable will run like n squared time if we find overall complexity of this for loop. we don't care about this return because it has lower complexity than this code, right? um, and and that's the reason why this pair variable has on square times space occupied when this code runs, right? If we plot it on the graph, what we're essentially doing is how long the n grows, right? So n grows from 0 until n squared time, and then at the same time this single unit space operation is going from 0 until n squared time, right? All right. We're gonna find out the space complexity of this program. We have a variable here, and then this loop runs from 0 until 2 raised to n. So this is 2 raised to n. That means it's gonna grow from 0 to 2 raised to n iteration, and if there's one statement that runs 1 unit of space multiplied 2 raised to n times, therefore the overall complexity of this for loop will be 2 raised to n, order of 2 raised to n, right? Exponential space. If you plot it on the graph, it's gonna go look like something like this, right? And the last one is factorial space, right? So look at this. This is a really simple code, right? And here we can split into two, right? So this is if condition. If yes, if n less than 1, this will execute. If n is greater than 1, then this will execute, right? And what does this do, right? So let's say n equals 5, right? What happened at this time when n equals 5? So we're inside this program and n less than equal 1? No, right? Because n equal 5. In that case, n is what? 5? 5 into, it's gonna call the same function by passing 5 minus 1, which is 4, right? So we have 5 times 4. It's gonna call the same function again. Again, this condition is false. Now the n is 4. 4 times 3. Again, it's gonna call 3. 3 times 2. Again, 2 times 1. And now 1. N equals 1. That's why it's written 1, right? So basically, we're doing 5 times 4 times 3 times 2 times 1, right? And which has n factorial, right? And because it's calling the same function, this is a call stack, right? If you draw call stack like this, right? In that case, the first call stack, let's say it's 5 times 4, right? And the next time when the function call, it's 4 times 3. The next time it's goes like 3 times 2, and then 2 times 1, and this length of this call stack, right? That's what we're interested here, right? And this, because it's running n times this factorial, that's why overall complexity of this program is order of n factorial, right? Alright, I hope you enjoyed this video. Please like and subscribe, and stay tuned for my next videos.